Welcome back to my lectures on groups, rings and fields. Our next topic is permutations. We've been talking about several groups. We have done lots of abelian groups. Most of the groups we discussed so far are abelian groups except the group of n by n invertible matrix with real entries is not an abelian group under matrix multiplication. But this group is infinite. Infinite non-abelian group. In this chapter of permutations, what we are trying to do is to create a finite non-abelian group. For that, we are going to use the permutations which you already learned in elementary algebra. A permutation is, by definition, is a bijective map from a set to itself. Well, though the permutations can be on an infinite set, what we are trying to do here is from a finite set to another finite, to itself. So, for all the discussions under the permutations, I am only considering finite sets, permutations on finite sets. Finite sets means it has got some n number of elements. But I am not interested in what that elements are. So what I will do is, for every finite set, I am going to write it as 1, 2, 3, n. It could be anything else, but for our discussion, this is sufficient enough. So, permutation is a bijective map from a set of a finite set to itself. So, for example, one of the finite map would be, let's say, you are going to take n is equal to 3. So, we need to map 1, 2 and 3 to itself, to the same set, probably 2, 1, 3. So this is how we are going to represent a permutation. Within a bracket, this is a source and this is our image of that map. So, our claim is, if you take the collection of all permutations from a finite set to itself, we can form a group with the binary operation as the composition of this bijection. Meaning, let us say you take two permutations from a set of set with 3 elements. For example, sigma is a map, is a permutation from 1, 2, 3 to 1, 3. This is a map, and we will take another map like 1, 2, 3, 2, 3, 1. These are two different permutations on the set of 3 elements. So these are our objects in the group, the elements of the group. The elements in the groups are the permutations. So we are going to define a binary operation here. Let us say sigma sigma after mu. We are composing mu with sigma. So this is going to be another permutation, and that is going to be, see, first we have to find out what is the image of this composition. So the composition goes like this. First you take the image of 1 under mu, that is 2. Then the image under sigma. So that is going to be 1. 2, 3, 3, 3. So this is 3, and this is automatically, this will become 2. Because 3, 1, 1, 2. So this is our binary operation. So our claim is that the collection of all permutations on a finite set of n elements forms a group under function composition. And it is called the symmetric group. With n elements, and it is denoted by this. See, we are going to prove that this is a group. I'm just giving you the plan of what we are going to do. So let us start proving that result. So the theorem. Let A be a finite set of n elements, and SA be the set of all permutations on A. Then SA or Sn is a group under function composition. Well, we can probably define the permutations like this. Definition: a permutation on a finite set A is a bijective map from A to So in order for us to prove that this is a group, there are three things we need to prove. That is, four things. The binary operation, the function composition is closed. Second one is function composition is associative. And third one is there exists a identity permutation. Then fourth one is for every permutation there exists an inverse. Well, these two are trivial from the elementary algebra because this is a function, and by the definition of the function it says it is actually a closed, it is closed. Because if sigma mu belongs to Sn, then sigma of mu is another bijective map and hence it is closed. And all bijective maps from a set to itself is always associative. I'm not going to prove this one because you can verify taking elements and see whether you are getting the same result when you have sigma of mu of tau of an element is equal to sigma mu of tau of an element. Actually, you can write it like this. Sigma of mu of tau of an element is equal to this. You can verify that. I'm not going to try that because this is coming from an elementary algebra. Identity, of course, the identity map is going to be I from A to A defined by I of an element is equal to A is a bijective map from A to A, and hence it belongs to S. And sigma of I is equal to I sigma is equal to sigma for all sigma in Sn. That's no problem because it is not moving with this identity you are not moving any element. So the only thing which we need to prove is for every element there exists a inverse. That is also trivial because for every bijective map from a set to itself has an inverse defined by probably how do you define this? If sigma inverse is defined from A to A by sigma inverse of A is equal to B if sigma B is equal to E. That is how we define. So this is a well-defined binary operation which is enjoying all the properties of a group. And that means Sn, from here on I will not use this notation, I will use only the notation Sn. So Sn is a group under permutation. And there are n factorial elements in this group. Because the number of ways n elements can be arranged from n elements is n factorial. And this is also called, Sn is called the symmetric group. Symmetric group. Let us take a close look at S3 and S4. S3 contains all permutations on a set of 3 elements. So, and it should have 3 factorial elements. So 3 factorial means 6 elements. So one of them will be definitely, we'll write it like this. One, two, three, and this is our I. Now what we are doing is, we'll write it as sigma 1 is 1, 2, 3, 2, 3, 1. And sigma 2 is 1, 2, 3, 3, 2, 1. And we need to define 3 more, and that is mu1 is equal to 1, 2, 3, 1, 3, 2. And mu2 is equal to 1, 2, 3, 2, 3, 1. 3, 2, 1. Now this is going to be 1, 2. And sorry, this is mu2. Mu3 is going to be 1, 2, 3, 2, 1, 3. Oh, this is actually 3, 1, 2. That is, I'm sorry. This is 3, 1, 2. And this is going to be 3, 2, 1. Okay. Now it's good. See, the reason for writing it like this is because it has got some geometrical implications. Let us consider these three numbers as the vertices of a triangle, a polygon with three elements. So 1, 2, 3. So the first row is this. The second row is another triangle which is going to be equilateral triangle, regular polygon, which is going to be put on top of this in a different order. The first one is, it is exactly the same. The source and the images are same. You are keeping the triangle exactly like on top of it. Here, what I'm going to do is, I'm going to rotate clockwise direction just one time. So 2 will go here, 1 will go here, and 3 will come here. So 1 goes to 2, and 3 goes to 1. So this is going to be 2, 3, 1. So this, see, if you turn like this, this is going to be 2, then this 2 will go here, so 3 will come here and 1 will come here. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. And you rotate one more time, you'll get this. So these are called rotations. But if you come here, this is less, this is different. This, what I'm going to do is, I'm going to draw the angular bisector here. This is a angular bisector of 1. Then twist it based on this. So you keep this one as it is, but you this twist here. So 1 goes to 1 because I'm not going to change 1. This is the axis which you are going to rotate. So you are going to take the image of this. So this will be, you are flipping based on this axis. So 1, 3, 2. So 1 goes to 1, 2 goes to 3, and 3 goes to 2. And that is this. So these are all mirror images. But in general, an SN can contain more elements than this. But for S3, it contains only rotations and mirror images. So this contains, from here onwards, when you are referring to a symmetric group with 3 elements, we always say this is actually, it's not just, we will write it as sigma 0. So sigma 0, sigma 1, sigma 2, then mu 1, mu 2, and mu 3. But when you take S4, not S3, S4, now we are talking about a polygon of 4 vertices. But the rotation is going to be the same. 1, 2, 3, 4. So rotation is going to be same. So you'll have 4 rotations. So we'll select as sigma 0, 1, 2, 3, 4. 1, 2, 3, 4, which is the identity. Sigma 1 is equal to 1, 2, 3, 4, 2, 3, 4, 1. Sigma 2, 1, 2, 3, 4, 3, 4, 1, 2, and sigma 3 is equal to 1, 2, 3, 4, 4, 1, 2, 3. Keep on rotating this. One example would be this is going to be this is going to be 2, 3, 4, 1. Your clockwise, or this is, I'm going to turn it as anti-clockwise direction. So these are all rotations. Doesn't matter which direction you are rotating, you'll get the same rotations. So these are rotations. But for mirror images, here I did only angle bisector. But here it's a combination of angle bisector and the divider of the sides. Because if you draw an angle bisector here, that is not going to hit another vertex. It is going to hit the, see, when the number of vertices are odd, you need to take only the angle bisector. But here, if the number of elements are even, then the angle bisector will go to the other one, and this angle bisector will go to this. So the mirror images mu1 angle bisector is going to be like this. Mu2 is going to be like this. 1, 2, 3, 4. 1 goes to 3 and 3 goes to 1. 2 goes to 4, 4 goes to 3. No, not like that. Not like that. I'm sorry. If you draw an angular bisector here, these two are fixed and these are turned. So this will be 1, 3, not change, but this is going to be 4, 2. And if you take this as fixed and you are changing the other one, then 1, 2, 3, 4, then this will be 2 and this will be 4 and this will be 1 and this will be 3. That is angle bisector. But you get another kind of symmetry here. That symmetry is the perpendicular bisector of each sides. So you turn like this. So it will be 3, 2, 4, 1. So that is actually called delta 1. 1, 2, 3, 4, and 1 goes to 3, 2 goes to 2, I'm sorry, this is, I had to, okay, just a minute. This, if you are taking the perpendicular bisector like this, so this will be 2, 1, 3, 4. So 1 goes to 2 and 2 goes to 1 and 3 goes to 3, 3 goes to 4 and 4 goes to 3. And you can have another perpendicular bisector like this and take the image on top, flip vertically, then this will become 4, 3 and this will become 1, 2. So 1 goes to 4, 1 goes to 4, and 2 goes to 3, and 4 goes to 1, and 3 goes to. So these are symmetric permutation within this group of permutations, symmetric group. So these are called dehydral subgroup. This is actually a subgroup. There are more permutations on S4 than these 8. S4 definitely contains 24 elements. That is 4 factorial elements. Actually, that is 24. What we are showing here is only 8 elements. So this is actually a subgroup of S4. Here we are doing the same thing, but the dehydral group is same as S3. Normally the dehydral group is denoted by Dn. So S3 is equal to Dn. Sorry, D3. But D4 onwards, it's always going to be a proper subgroup of, Dn is going to be a proper subgroup of Sn for all n greater than . So the number of elements in the dehydral group is going to be, see how we are going to get here. You have, if we'll wipe it off, and so dehydral subgroups of Sn is a subgroup of Sn formed by rotations and mirror images, considering the elements of the n elements, considering the n elements as the vertices of a regular n-gram. So for when n is odd, dehydral subgroups contains n rotations and n mirror images formed by the angle bisectors. Okay? When n is even, then dehydral subgroup contains n rotations and, or we'll write it as 3 terms, n rotation n by 2 mirror images formed by angle bisectors and n by 2 mirror images formed by the side side bisectors. So the number of elements in Dn is, well, and is denoted by, we'll say, and is denoted by Dn. The number of elements in Dn is n plus n is equal to 2n. Here the number of elements in Dn is equal to n plus n by 2 plus n by 2. Still it is 2n. So our next attempt is to show that Sn is really a non-abelian group when n is greater than or equal to 3. So Sn is non-abelian when n is greater than or equal to 3. We know that if n is equal to 2, it is abelian because there are only 2 permutations in S2 and they commutes. So to prove that Sn is non-abelian, what we need to do is we need to find out 2 permutations in Sn that will not commute. So let sigma and mu be 2 permutations in Sn defined by sigma of 1, sigma of 2, sigma of 3. This is actually going to be 2, this is going to be 3, and this is going to be 1. And sigma of n is equal to n for all n not equal to 1, 2, 3. What I am trying to say here is, it is not just S3. It could be any permutation in any symmetric group more than n elements, more than 3 elements. So let us see in S6 how this is going to happen. S6, 1, 2, 3, 4, 5, 6. So these 3 elements are not moved. But here, this is going to be 2, and this is going to be 3, and this is going to be 1. So this is the permutation I am talking about. And if you take another one, F5, then this is the permutation I am talking about. This is in S5, and this is in S6. And mu is defined as, this is mu of 2 is equal to 3, and mu of 1 is 1, and mu of 3 is equal to 2. Now we'll see sigma mu of 1 is equal to sigma of mu of 1, and that is equal to sigma of mu of 1 is 1 and sigma of 1 is 2. Now we'll see mu of sigma of 1 is equal to mu of sigma of 1, and that is equal to mu of sigma of 1 is 2 and mu of 2 is equal to 3. And that means sigma mu is different from mu sigma. That means Sn is non-abelian when n is greater than or equal to 3. Now let us compute all the subgroups of S3. Let us compute all subgroups of S3. So what are the elements in S3? S3 contains sigma 0, sigma 1, sigma 2, mu 1, mu 2 and mu 3. Where sigma 0 is equal to 1, 2, 3, 1, 2, 3. Sigma 1 is equal to 1, 2, 3, 2, 3, 1. Sigma 2 is equal to 1, 2, 3, 3, 1, 2. And mu 1 is equal to 1, 2, 3, 1, 3, 2. Mu 2 is equal to 1, 2, 3, 3, 2, 1. And mu 3 is equal to 1, 2, 3, then 2, 1, 3. Now, what we need to do is we'll write the multiplication table. Sigma 0, sigma 1, sigma 2, mu 1, mu 2, mu 3. Sigma 0, sigma 1, sigma 2, mu 1, mu 2, mu 3. And this is definitely going to be sigma 0, sigma 1, sigma 1, 2, mu 1, mu 2, mu 3. And this is going to be sigma 1, sigma 2, sigma mu 1, mu 2, and mu 3. So I'm going to show how to compute these composition of permutations, but I'm not going to do everything here. I'm going to write down the result. But first let us compute sigma 1 square. Sigma 1 square means you are composing sigma 1 to itself. So 1 goes to 2 and 2 goes to 3. So this is going to sigma 1 square is going to be 1 goes to 2 and 2 goes to 3. 2 goes to 3 and 3 goes to 1. And 3 goes to 1 and 1 goes to 2. and that is nothing but sigma 2. So here you are going to have sigma 2, and here you are going to have sigma 0. See, if you take these two together, one goes to, if you take these two together, 1 goes to 2, 2 goes to 1. 1 goes to 2, 2 goes to 1. So this is 1, 1. 2 goes to 3, and 3 goes to 2. So 2 goes to 2 here, and 3 goes to 3. And that is why I said it's sigma 3. And this is going to be sigma mu 3, mu 1, and mu 2. And this is going to be sigma 0, sigma 1, two, 3, 1. And this is going to be mu 2, mu 3, sigma 0, sigma 1, sigma 2. Then 3, 1, and the last one is mu 1, mu 2, and this is going to be sigma 1, sigma 2, and sigma 0. Then if you want to find out, see, if you, the subgroup of ST should be of order either 1 or 2 or 3, because the subgroup, the order of subgroup should divide the order of S3, and which is 6, and the last one is 6. So S3 will be here and the identity map will be here. That is actually sigma 0. And there is only one, you can verify this, there is only one subgroup of order 3, and that is sigma 0, sigma 1, and sigma 2. And there are 3 other subgroups of order 2, and that is sigma 0, mu 1, sigma 0, mu 2, sigma 0, mu 3. To verify this, see this, if you take this square, you won't see any sigmas, sorry, any mu's, only sigmas. So this is totally it's a subgroup of S3. Sigma 0 and mu 1. Sigma 0 and mu 1, this is this. And sigma 0 of mu 1, this is again. So if you combine these two, sigma 0 and mu 1 times mu 1 is sigma 0. And that is this one. If you don't want to do like this, what you can do is find out all the subgroup generated by each element. So what I'm saying is the subgroup generated by sigma 0 is going to be just sigma 0. Subgroup generated by 1 and 2 is going to be sigma 0, sigma 1, sigma 2. And the generated by mu 1 is going to be sigma 0 and mu 1. Why? Because mu 1 square is 0. Mu 1 square is the identity map. So mu1 to mu2 or the subgroup generated by mu2 is equal to sigma 0 mu2 because mu2 times mu2 is sigma 0. Similarly, mu3 times mu3 is equal to sigma 0. So these are the possible subgroups of S3. Let us do a computational problem on S6. Compute sigma inverse mu sigma square and the order of the subgroup generated by mu square on S6 where sigma is equal to 1, 2, 3, 4, 5, 6, 3, 1, 4, 5, 6, 2. Mu is equal to 1, 2, 3, 4, 5, 6. 2, 4, 1, 3, 6, 5. So this is just a computational problem. Just want to make sure that you got the idea of composing two permutations. So sigma square is going to be 1, 2, 3, 4, 5, 6, 1, 3, 3, 4, 2, 1, 1, 3, 3, 4, 4, 5, 4, 5, 5, 6, 5, 6, 6, 2, 6, 2, 2, 1. Now you are composing this one with the mu. So 1, 2, 2, 3. So mu sigma square is equal to first sigma square. So 1, 4. Let's write 1, 2, 3, 4, 5, 6. 1, 4, 4, 3. 2, 3, 3, 1. 3, 5, 5, 6. 4, 6, 6, 5. 5, 2, 2, 4. 6, 1, 1, 2. And what is sigma inverse? Sigma inverse is 1, 2, 3, 4, 5, 6. One goes to 2. 2 goes to 6. 3 goes to 1. 4 goes to 3. And 5 goes to 4, and 6 goes to 5. That is sigma inverse. So, sigma inverse of mu sigma square is going to be 1, 2, 3, 4, 5, 6. 1 goes to 3 and 3 goes to 1. 2 goes to 1 and 1 goes to 2. 3 goes to 6 and 6 goes to 5. 4 goes to 5 and 5 goes to 4. 3 goes to 4 and 4 goes to 3. 6 goes to 2. 2 goes to 6. So this is the permutation of sigma inverse mu sigma square. Now we need to find out mu square. What is mu square? Mu square is 1, 2, 3, 4, 5, 6. Generated by mu square. So first you need to find out mu square. Mu square is 1, 2, 2, 4. 2, 4, 4, 3. 3, 1, 1, 2. 4, 3, 3, 1. 5, 6, 6, 5. 6, 5, 5, 6. So now if you want to find out the subgroup generated by mu square, you need to say mu to the power of 4. 1, 2, 3, 4, 5, 6. 1, 4, 4, 1. 2, 3, 3, 2. 3, 2, 2, 3. 4, 1, 1, 4. 5, 5, 5, 5. And 6, 6, 6. So this is actually nothing but 0. Or probably the identity map. We'll call it as identity map. So the subgroup generated by mu square has only 2 elements. That is I and mu square. So the order of subgroup generated by mu square is